反对明写上去。
写对名。写边一层。好，这边这边。
Okay, reporter, present.
Distinguished juries and fellow debaters. I'm the reporter for ring order from C-jeleskedik. So let's start with the proper statement. An oil horizontal cylindrical shaft rotates on its axis at constant speed. Make a ring from a cardboard disc with the inner diameter roughly twice the diameter of the shaft, and put a ring on the shaft. Depending on the tilt of the ring, you can travel along the shaft in either direction. Investigate the phenomenon. Based upon the problem statement, there will be two main focuses to be discussed in the reporter's report. First is, of course, the tilt of the ring. Second is the ring's motion along the shaft. And then we're trying to find out the relationship between the two factors. Now let's take a look at the presentation's outline. We'll start with the observation of the ring's motion, moving to our theory part, and then we'll introduce our experimental setup, and then we'll introduce our experimental results, then reach the conclusion. So here's our observation video. If we look, as you can see, then the ring will travel along the shaft in either direction. And if you look at the ring from above, then you can clearly see that the tilt of the ring changes as the ring travels in either direction of the shaft. Now there will be three features to be discussed in this presentation. First, of course, is the motion of the shaft, as since we had observed in observation video. Second is the angle phi, which is if you look at the ring from above, then we will name this angle as phi. Then if you look at the ring from horizontally, then we will name the tilt here as angle theta. Here's our observation. As you can see, when the ring started to go along the shaft, and the displacements will increase this. And then when it's in the middle of the shaft, as you can see in the SD chart, the velocity will reach its maximum. And then when it reaches the end of the shaft, which is here, then the velocity will equal 0. When it goes back, the velocity will reach its maximum again. Now here's observation. As you can see in the picture, the tilt of the ring will changes as it travels along the shaft. Here, we use angle phi as I have previously introduced. Now here's the trend of the change in angle phi. First, angle phi will increase and then reach its maximum, and angle phi will decrease. And if we look at the whole system here, then first, of course, when it travels through the middle of the shaft, the velocity will reach maximum, and the angle phi, the vertical tilt, will reach maximum in the absolute value. And then when it travels to the end of the shaft, and then the velocity will equal 0, and angle phi will equal 0, and vice versa. Now let's move on to the theory part. First of all, we'll like to introduce the effect of perturbation. If we place a ring vertical to a shaft and the ring is stilled, then of course the angle phi will equal 0. But when the ring started to rotate, as you can see here in the video, then the perturbation from the motor and the shaft will result in an increase in angle phi. And as you can see in the video, they'll have a change in the velocity of the ring along the shaft. So the ring will start going here. Then if we look, now I'm going to introduce my angle theta, because angle theta will play an important role in the later part of my presentation. First of all, we will have acceleration in the process, so you can see the ring is stilled, and then it will move through the one direction of the shaft. And the ring has its own inertia. As a result, the angle ring will tilt horizontally as a result, resulting in a change in angle theta. And as you can see in the chart, when the acceleration is positive, then the angle theta will increases, and then when the velocity goes down, the angle theta will go down. Now here we're going to try to find out the connection between the two angles. Now since the ring will tilt horizontally, then they will have a torque whose direction is directed into the paper, like this way. And then, based upon that, this is the torque's direction, is into the paper if we look at the ring from above. Now the ring will derive angular momentum from its rotation. And since the torque will affect the angular momentum, it will form a new angular momentum, resulting in the ring to tilt harder. The ring will tilt harder. Thus, the angle phi that we define here will increase. Now, when the angle theta increases, if you look at the ring from the x-axis perspective, if you look at the ring from the shaft, then the ring will have one intersection with the shaft. But when the angle phi reaches its maximum, as you can see in the video, then it will have two intersections with the shaft. Then the reaction force from the rod will make the ring have a change in its direction, as you can see here in the video. So if you look at the phenomenon as a whole, when the angle theta will increases due to the phenomenon of precession, and then it will reach two intersections with the shaft. And then the reaction force will make the angle theta decreases. And then it will go down as a circle. As you can see here, the angle theta increase, decrease, increase, and decrease. Now we're only trying to figure out why the ring can travel along the shaft. And if you rotate the ring slowly, then you can find out that the ring follows the spiral route along the shaft, as you can see here. It goes like this. And then if you expand the surface of the shaft, and then you will find that the ring forms an oblique line from the top to the bottom, which here the angle phi, we define here, also appears. So based upon that, the ring will have a motion along the shaft, as it suggests here. Now, if the angle phi is bigger, then the ring will have more displacements along the shaft, resulting in the increase in velocity. So as you can see in the chart here, when the angle phi increases in the absolute value, the velocity of the ring also increases. And then, when the angle phi decreases, the velocity of the ring also decreases. And as we previously introduced, then the change in velocity will also result in the acceleration of the ring. Then will result in the effect of precession. So the ring's motion is like a circle that goes on and on and on and on. Now I would like to move on to our experiment part. I would first like to introduce the experimental setup. As you can see, a shaft is connected by the bearing and the motor. And then here we use the metal ring as experiment we use the metal ring to do our experiment. Since the metal ring is more static, it can represent the phenomenon better, so we use the metal ring. And then here's our experimental result. So if we turn on the rotational speed of the shaft, then as you can see, the period will go up. Since if the rotational speed goes up, the angular momentum of the ring will go up, making the ring harder to turn the angle phi. As a result, the period will go up. But when the rotational speed reaches a certain value, then when the rotational speed of the ring goes down, then the period will go down. And I will explain the reason in the next slide. Here's the change in angle phi with the rotational speed. As you can see, when the rotational speed increases, the change in angle phi will decrease. Since if the angle phi, let me use my prop here. As we had introduced before, that this here, it is the angle theta we defined. If you look at the ring from above, here, it is the angle phi. And since we know that the rotational speed if it is faster, then the angle theta will increases. When the angle theta increases, as you can see here, then the angle phi they can change. So it does not have that much room for the angle phi to change. Okay, so right now result in a decrease in period. Now let's reach to a conclusion part. First of all, the perturbation will cause the initial angle phi to have a change. So the ring will start to tilt horizontally. Then, due to the effect of precession, then the angle phi, then the vertical angle will start to tilt hard, will start to increase, as you can see here, due to the effect of precession. When it reaches its maximum, the ring will have two intersections with the shaft. The reaction force from the rod will result in a decrease in angle phi. As you can see here, here it is a part that has two intersections, and then since then, the angle theta will decrease. Increase, decrease, increase, decrease. That's the motion of the ring. And here's the conclusion for the motion. As we have previously introduced, that if the angle phi is bigger, then the ring can have a bigger displacement along the shaft. And we can observe from the VT chart and the change in angle phi. If the angle phi is bigger in absolute value, then the velocity will be bigger. And finally, it's the experimental part. Since then omega will increase, then resulting in the ring harder to change the angle phi. And so resulting in the period goes up. But when it reaches a certain value, due to the increase in angle theta, then there's not much room for the ring to have change in angle phi. So the period of the ring will go down. So here at the end of the speech, I would like to emphasize is that the whole motion of the ring is like a cycle. So as you can see from the previous slide, the change in angle theta will result in the increase in velocity of the ring, and the velocity of the ring will result in the precession, and then you will affect one another as the ring travels along the shaft. And that's the end of my presentation. Thank you.
Let's go to the next stage. Opponent has the question.
But change the page, the statement page. Maybe
From the statement?
Okay, we can see the problem of them making a ring from the cardboard disc, but in your experiments.
Okay, so that's a really good question. For this question, seems that as you can see in the observation video, that both the ring from cardboard and the ring from metal will have the same phenomenon. And since that the ring made of the metal can represent the phenomenon better, so we use metal as our experimental tool. And then we believe that the difference between the cardboard disc and the metal disc is only the change in the mass of the ring.
So could you turn to page 15? That's the problem I want to discuss with you in next class. And I just tell you, and I am not so.
So you are not
ask you to explain it more clearly.
Oh, of course. Okay, so do you want me to explain now or later?
Or maybe later.
Okay, so what's the next question?
Okay. So could you show a video of your experiment?
This one?
No, opponent has 3 minutes to prepare.
27。
基本跟体育的技术的中间这个就没差。这个数字是
Opponent has 4 minutes to present your case and discussion. Go ahead.
The first statement is an order per lactose cell derivative shaft rotates around its axis at constant speed, make a ring from a cardboard disc and with the inner diameter roughly twice the diameter of the shaft and put the ring on the shaft. Depending on the tilt of the ring, it can travel along the shaft in either direction. Investigate the phenomenon. As the theory reporter refers is the speed will reach the maximum in the middle of the shaft. The acceleration and inertia causes the change in angle theta and angle phi increase. To intersection, angle theta increases. And when angle phi increases, the speed increases. And the experiments for reporter do is when the rotational speed goes up, it will make the period goes up. But when it reaches a certain rotation speed, the increase in angle theta decrease in change of the angle phi and decrease in period. And that's perturbation because the initial angle phi and precision and two intersections. And so this is the problem I want to discussion with reporter. And first is how do you make the chart in page 7, and maybe we can discuss separately. how do you check the angle you set in the beginning in 0? And maybe we can just, I talked to you earlier that the page 15, and I also want to discuss with you if you, because your experiment don't have the board beside it, so how to explain the ring will turn to other direction? Maybe it will go just one way.
Go to the next page, please. Go ahead. Go ahead.
Also, maybe we can discuss about the page 15.
Okay, so first of all, let's start with page 14. Since so do you understand why there is an angle? The ring will tilt horizontally. Okay. So since then the gravity will form a torque, which direction is into the paper. So do you understand this part? So the gravity will form a torque.
Yeah.
Okay. So since then, if you look at the ring from above, then the torque from gravity, and then the ring will acquire angular momentum from its rotation. Instead, if the ring rotates into the paper, then the ring will also rotate into the paper. Then they will have an angular momentum of which direction is here, this way. And then the torque will cause a change in angular momentum of which direction will be this way. Will be this way. So then the ring will tilt harder. So that's why the ring will increase. And as you have mentioned, that maybe the ring will just continue goes on and it will not have a turn in the direction. And since the angle theta will cannot, there's the ring, and if the angle theta keep increasing, then the ring will hit the shaft, as you can see here in the video. Sorry, I apologize for the technical problem. So first of all, then if they have two intersections with the shaft, then the reaction force from the rod will make the ring have a turn in the direction, which is the part that we can see in the observation video. Whether it's about the metal ring or the copper ring, that you will all have a turn in the direction. Since the ring travels from one side to the other side, you will have a turn in the direction. Did I answer your question?
And so, because in the statement it wants us to use the
copper ring.
but the difference is iron.
Oh.
So I want to maybe could you explain how you correct?
Oh.
Because if the red is the paper and the oil, maybe it will on the inside.
Oh yes. That's one of the part. That's a very good question. Thank you, opponent. Since then, since the reporter believe that the difference between using the copper disc and the metal disc is the change in the mass. And as you can see in the observation video, both the metal ring and the copper ring have the phenomenon that the problem statement suggests. And since the metal ring, since if you use a copper ring, then the mass is less, then the torque from gravity won't be that much of the metal ring. So did you follow? Did you understand what I'm talking right now? Since the precession, which is the change in angular momentum, will affected by the mass of the ring. Did you understand? Yes. So the reporter believed that the phenomenon of precession will not be that easy to be represented by the copper ring.
So have you tried the material of the statement?
Oh yes, of course. Since as you can see here, the observation video is the one of cardboard, is the cardboard ring. Sorry for not clarifying your doubt in the previous discussion.
I mean, that is this video about not maybe not iron.
Can you repeat your question again?
I mean not exact this video. Have you tried other
Rings. You mean change in the mass of the ring or the diameter of the ring? Is that what you are talking about?
mass of ring?
Oh, mass of a ring. Okay. Since that we cannot really find that, since that the density of cardboard it does not really matter from one another. So if we want to change the mass of a ring, then one way is to increase like the diameter of the ring, but then will also result in the increase. It will also affect the moment of inertia of the ring. And we try to figure out a way that we try to make, if we want to add weight to the ring, then we cannot make sure that the weight can separate averagely along the ring. So that's the part that that's the question that we encountered. And that's a really good question that you brought up. Thank you.
Please turn to page 7.
Okay, page 7. Page 7.
So could you explain, because this chart is like a line, but
Okay.
in this it's
Oh.
just a dot.
Oh, okay. Thank you for the question. Since that we use checker to get the motion of the ring, so all of those are dots, but they are very close to one another, so you look like a ring. So both these two are dots. Yes, is that
So
yes.
each of the dots is mean what?
Okay. So we define here. This is the shaft. This is the x-axis, and we define here as 0. So here's the negative part. Here's the positive part. So when the ring from point 1 to point 2, it means that the ring travel from point 1 to point 2, and that's what this chart is about. And then when it travels from point 2 to point 3, that means that it travels from point 2 to point 3. And then this is x chart. When the velocity here the velocity chart means that if here's when the ring travels from 1 to 2, then the velocity will increases. And then if it travels to 2 to 3, then the velocity will decreases. This is what the chart is trying to represent.
So the red dot is about one.
Oh, the red dot is just a dot that we're trying to simplify. It does not belong to the graph. It's just like a dot we're trying to point out since that,
Okay.
yes.
Okay, thank you.
Thank you.
So the other questions.
Yes.
How do you check the angle you said in the beginning?
Oh,
is
you mean the angle
if you
phi?
would
Yes.
use your hand.
Oh,
Maybe
Oh.
if not.
yes, that's a question that we have been considered. Of course, that you cannot really place the ring that is absolutely vertical to the shaft. But of course, we're trying to make, here we are trying to introduce the effect of perturbation, meaning that with the rod spinning, then the angle phi will not equal 0. That's just the part that I'm trying to convey here.
Okay.
Okay, so.
I'm sorry, but
Yes.
I know maybe the experiment is the same, but I really
Yes.
want to know what maybe you use the cardboard, maybe
Yes.
the experiment results will different.
Oh, yes, but there is the possibility that experiment result will not be will be different. But since that just that you can see here that both the ring both the cardboard disc and the metal disc will have the same phenomenon and the same motion along the shaft. So the reporter believes that they will have the same phenomenon. The only differences is the mass of the ring. And by the way, the inner diameter and outer diameter of the ring, of the metal ring and the cardboard ring used in the observation video is the same.
So,
Yes.
how you change the
Yes.
iris inner diameter?
Sorry, I didn't change the inner diameter of the iron. So we try to have the metal ring whose inner diameter is twice the inner diameter of the shaft. We just make the iron ring. Is that your question? Okay. Okay, thank you.
Okay, let's go to the next page. For the summary, the discussion, 1 minute. Summary.
Okay. In our discussion, I asked the reporter about their experiment is different to the statements, and the reporter answered is I think the result may not be different, and I asked them about the chart making because they thought I think maybe the line will be more smoothly, and so they tell me they use tracker to analyze it, and okay.
Okay. Question for the reviewer.
Okay, so I'm the reviewer of this time, and I would like to go back to the problem statement. It is called the ring Euler,
Okay.
and it wants us to have a horizontal shaft.
Yes.
And in your presentation, I didn't hear you explain much about the effect of the oil. So do you think oil will have an effect on your theory?
Yes, since oil will result in the friction of the ring. So I believe that if it is unoiled, then the phenomenon of precision will not that much be easy to occur.
So it's only changes in friction.
Yes.
Yes. Okay,
Yes.
so what do you think about it?
Do you mean the
Will the oil change the phenomenon?
oil? I think it may change the phenomenon because I think oil may influence the friction between the ring and the shell.
Oh, so it's friction, right?
Yeah.
Okay, and for the report in your video, your shaft actually vibrates up and down, and that makes me doubt of your data.
Okay. So do you mean this video?
No, it's other videos.
You mean this one?
Yeah.
Oh, sorry. I apologize for the quality of the video. It's not that the shaft is vibrating since it's the camera we are filming vibrating. As you can see here.
Okay, I understand.
Okay, thank you.
Thank you. And also, please turn to page 15.
15.
Next one. Oh yeah, and stop. As you can see, this is the angular momentum, right?
Yes.
And here's the torque,
Yes.
right? But why are they in different direction?
Oh,
Because
yes.
the torque should be the change of the angular momentum. So why are they in
no,
different
because
direction?
the arises from two different factors. Since the torque is the result of gravity from my previous slides, and then as you can see here, this is the effect of gravity. And the angular momentum is from the ring's rotation. It's not the gravity, it's the ring's rotation. So the two arises from different factors.
Okay, I'll jump up to the next question. In your theory, you said in your observation the ring will go and turn back and turn back again, right?
Yes.
And why will it turn back?
Oh, as I mentioned before, since if the turn back or not is defined by the angle theta, sorry, not theta, phi here. So if the angle phi reaches its maximum,
Okay. Stop. What's the phi maximum?
What's the phi max? Can you clarify your question?
Can you calculate the phi maximum?
Oh, you mean is there an actual number of
Yeah.
phi?
Yes.
Okay, so I will answer that in the concluding remark. Thank you.
The opponent preparation for the review 2 minutes. Okay, the reviewer take the floor.
Okay, hello everyone. I'm the reviewer of this time, and I'm from Team Oops. Oh, and here's the problem statement. I want to emphasize the oil horizontal cylindrical shafts, and they can travel along the shaft in either direction. Good and straight. Okay, and here's the pros and cons for the report. The report can have clear observation on these phenomena, and he has clear explanation of these phenomena too. But the report lacks some mathematical equation to guide us to believe, and the materials and they didn't emphasize in his presentation, and they didn't provide clear approach until the opponent asked the report, and also they only test little parameters. I believe that there are more parameters that can be tested. Okay, and here's a summary of the discussion between the opponent and report. First, they discuss the material, which is iron or carbonics, will they affect the phenomenon. And the second is the angle. And the third is the approach, how could they measure the velocity and the angle phi and theta. And the fourth is that the initial situation, the initial angle may also affect the phenomenon. Okay, and here's the clash one. The opponent asks, why use an iron disc? Because the problem statement tells us that it is a cardboard disc. And the report replied that they believe that the iron and the cardboard discs are the same. They only difference in mass. And the reviewer thinks that they not only difference in mass, they also can affect the moment of inertia, the mass, and also the friction. And one important thing is that the cardboard may also absorb oil. That may also so that the mass will change. Okay, clash 2 is that the opponent asks us how could they measure the velocity, and the report replied that they use tracker, and I think that's no problem for the report. And it's clash 3, how to check the angle, and the report says that the initial angle is just used to interpret the concept. And the reviewer thinks that in the presentation of the report, they always say that the initial angle is 90 degrees. But we believe that the initial angle will not only be 90 degrees, they can also be like smaller ones. Okay, and here's the next point. As the problem statement says, it is a ring Euler, and both opponent and reporter says that the oil will affect the friction, but the reviewer thinks that because it is in the oil system, you cannot use friction as a model. You should use viscosity and lubrication to measure that, and that should be discussed in the discussion. And also, the report and the opponent doesn't discuss about the mechanics of the phenomenon. They only they didn't discuss why, and they didn't discuss about how does the force happen. And also, the report doesn't clearly explain why the cardboard turned back and forth, and the period of them, I don't know which the report said is stay the same or it was different. What do you think?
Reporter have 2 minutes to conclude.
Okay, so first of all, thank you for the opponent and reporter for this wonderful debate. But first of all, throughout the experiment, which the reporter has mentioned about is there a maximum for the angle phi, and throughout the experiment, that we did find out there's a maximum of the angle phi, since the ring cannot rotate infinity along the shaft. The shaft will block the ring from continue increase in angle phi. So about 60 degrees will be the maximum of the angle phi, and then we would try to check of 5 times, but we only use the data of 3 times since there will be too much dust on the graph. Allow me to apologize for that part. And then for the precision part, here if the reviewer is trying to mean that the direction in the change of angle momentum is wrong, then the reporter would like to apologize. It's just it should be here, so it is just a kind of like a typo. And then for the concluding remark, that the perturbation of the shaft will result in the initial angle phi, will cause the ring to move along the shaft. When the angle phi equals 0, then the ring will not move at all. It will just rotate at its own place along the shaft. And for more parameter parts, it seems that the only parameters that we can change is the rotation of the shaft. Since if we want to change the mass of the rings, then we cannot really find that the different density of the rings. Like we can use metal and cardboard and do the parameters. And then I just don't really understand the point stated that the reporter didn't mention the mechanisms of the phenomenon. And the difference of cardboard ring and the mass of a ring is, first of all, the cardboard both absorb the oil.
Okay, thank you.
Thank you.
Question from the jury.
I have a question for the reporter. Could you turn to page 40?
Yes.
Yeah, here you told us that the direction of the torque is
Yes.
actually going into the paper.
Yes.
Right? And could you go to the next page? So why the torque now is not going into
Oh, okay. So allow me to use my prop to explain. So let's previous stage. So if we look at a ring as this is the chart of a ring, as you can see, here's the horizontal view. And then next slide. And then if we look at the ring from above, sorry, I didn't clarify about this is the look at the ring from above. So if you look at the ring from above, then it will become like this. And then the torque of the gravity will be in this direction. So that's what I mean here. So that's, as you can see. Oh, okay. So can you understand what I'm saying?
Okay.
So thank you.
Any question for the jury?
You say something more about the force behind
Yes.
the motion.
The motion, yes.
Okay. Oh, okay. Since that if we through the observation video, if we rotate, I can demonstrate the phenomenon here. Since if the angle phi is not equals to 0, that if I have a tilt, then you will have a motion along the shaft. If I spin the shaft here, you can see that the shaft will have a motion. And then we found out that the shaft will have a spiral route along the shaft. Since if we take a paper and then we draw, and then since the shaft is not vertical, the ring is not vertical to the shaft, that will be like this. And then if we draw the root of the ring, and then we unfold the paper, and then we will find that the shaft of the root of a ring being an oblique line from the top to the bottom. That's what I'm trying to express here.
I understand you, but I have a similar question as these two.
Sorry.
So what's the why would it
Make a turn.
Okay, next turn. For the turn price about which I have previously introduced is I believe it's the effect of precession. Since that if I demonstrate the ring, this is the vertical view. Then this is the change in angle phi. Then if the angle phi continues to increase, then it reaches its maximum. Then you will have two intersections with the shaft. And then the shaft will apply a reaction force that make the ring turns back. And then if you...
Is that the force large enough to make a turn, or just slow it down?
Oh, so that's why we have the videos here. So, okay, so since the video is working, we have if the ring has two intersections with a shaft, then they will cause the ring to rotate. Sorry, not rotate, have a change in the direction, and that's the part.
Did you actually observe the 2-point contact?
Can you
Did you actually observe the
In your video.
2-point contact?
Oh, because we try to film, but the second that it has two intersections is too fast, so we cannot really get the actual picture.
Okay, thanks. Okay, that's all. Yuri? Are we ready? Okay, let's go ahead. For the reporter, Knight 8777.
Thank you, Professor.
For the reviewer, opponent, sorry. 66565. For the reviewer, yes. 87797. Okay. Reporter takes the floor to give you a presentation.
Hello everyone, I'm Arthur Tsai from NKIH, and the name is U-蘋果bang你. And today our topic is drinking straw. So let's look at the problem statement first. When the drinking straw is placed in a glass of a carbonated drink, it can rise up, sometimes toppling over the edges of a glass. Investigate and explain the motion of the straw and determine the conditions under which the straw will topple. So the key point is, first we've got explain the motion of the straw. Then we need to determine the condition whether the straw will topple. This is basically my outline. First we will do some investigations. This involves I will give a video to observe easily, and then I will talk about the theories of this, and then we will do some experiment, and after the experiment we'll give some conclusion. Okay, so the investigation first. So we throw the straw in there, and as the time goes, maybe it's not so, and let's make the video over. Okay. During the video, we can see. Okay. During the video, we can see that as the straw puts into the carbonated drinks, the bubbles of the blisters of the carbon dioxide begins to attach on the walls of the straw. And as the time goes, and the bubbles gets bigger, and eventually when the bubble is big enough, it gives bouncy and that will let the straw topple. So look at this picture now. The BS that we said is the bouncy of the straw the bouncy of the straw, and the BV is the bouncy of the carbon dioxide bubble that it will attach on the straw and will give force to the straw. And the F is the friction of the beakers gives to the straw. Like it will give a force that will stop the straw from toppling. And the mg is the very center of the straw. And we can see here's the point of the straw, so that we can so the main theory of here is the BS, the bouncy of the straw, and the bouncy of the carbon dioxide bubble, plus the very center of the straw, is a clockwise force, and the friction is a counterclockwise force. So like when the friction is smaller than these three forces, the straw will start to move up and eventually topple. So let's walk into the experiment. Our experiment setup is the beaker, straw, carbonated drinks, which we said only one kind, apple cider, and the timer used to record the time where the straw will topple, and then a camera for recording the video. There are some prerequisites before the experiment. These are the other threes that we set, and we never changed them. The size of the straw, and the types of the carbonated drink, as I just mentioned on the previous page, and the size of the beaker. Okay, so these are the possible parameters that we will do experiment for. First is the volume of the carbonated drink, then the length of the straw, then the amount of carbon dioxide in the drink, and the last, the temperature of the drink. So experiment number 1, the volume of the carbonated drinks. We change the volume of carbonated drinks and record the time that the straw will topple. Because of the size of the beaker is the same, so we just change the depth of the carbonated drinks just like this here, and we place a ruler up there, and it's 9 centimeters, 10 centimeters, and 11 centimeters. We can now by changing this volume, we can investigate this. And after the experiment, we got this data. we can see it clearly that the 11 centimeters will take the least amount of time to let the straw topple, and as for the 9 centimeters, it takes a lot of time than the 11 centimeters. And we actually did this kind of experiment 5 times in the same condition, and so this is the original data that we have. And the previous page is the average of these 5 data. As for the experiment 2, the length of the straw, we change the length of the straw and record the time when it would topple. Next one. This is the data that we have. We start from 45 centimeters straw and make it down to 31 centimeters. And we can see the graph. We can see this graph is rise up in we can see that as shorter the straw is, we can see that it takes longer to let it topple. And there's some problem in here, and we think it's an error or what. Like we can see when the 41 centimeters takes this, then the 42 centimeters as well as the 43 centimeters. We think this kind of experiment is every time, when the condition is the same, we think it's randomized, like when the amount of bubbles will be clear on the wall of the straw. So this is what we think that makes this graph look like this. And for experiment 3, the amount of carbon dioxide in the drink. First, the amount of carbon dioxide in the drink will decrease after it's poured. It's basically easy to understand. So we put the straw into a carbonated drink over and over to see the time. Over time changes as the carbon dioxide decreases from the drink. And so we got a graph from here. Same as the experiment 2, we have seen that the graph changes. The graph can change as there's some problem in here, like when the experiment 10 takes less than experiment 9. So as I just mentioned, it's probably the randomized bubble that will attach on the wall. This all. And for the experiment 4, the temperature of the drink. So we use two beakers and 2 carbon dioxide with different temperatures, and record the time of straw it will topple. Like I just said, 42 carbon dioxide drink, which is different temperature in the same time, in 2 different beakers, and we throw the straw in the same time and record it. So we got a graph like this. As you can see, the cold one takes more time. The cold one takes more time to let it topple. And when it comes to experiment 10 or 11, we can see that the normal state takes a lot of time than the cold one. And you can see the cold one seems very average. That's because of the temperature will affect the amount of carbon dioxide in the drinks. So when the cold is normal, when we pour into it, at first the carbon dioxide will decrease much more than the cold drinks. So in the end, there will be a little of carbon dioxide left, and it took a lot of time to make the straw in the normal temperature to let the straw topple. So after all these experiments, we got the conclusion of it. If there is enough carbon dioxide blister, and there will be enough balance, then we know that it will cause the straw to topple. And to the second point, more carbon dioxide blister, the bouncing will be bigger, and the straw will topple faster. As for the last one, as the length of the straw gets shorter, the straw will topple in a short amount of time. Just as we did for the experiment 2. And that's my presentation. Thank you.
Question from the opponent, 2 minutes.
Okay, first I'm going to ask about your hypothesis.
Okay.
And can you quantify the initial quantity of the carbonate in the water?
No, just as mentioned, we think it's randomized. So
Okay,
it's,
thank you.
yes.
I know. And another question is, do you think the sugar water filled with carbonate is the same as the pure water filled with carbonate? Yes or no?
I think the main point of this is the
Just answer
amount.
me yes or no.
Amount. Okay. Can you repeat your question again?
Do you think the sugar water filled with carbonate will cause the same effect as the pure water filled with carbonate?
Yes.
Yes. Okay. And I want to ask about next questions. And do you think the surface tension play a major role in this phenomenon?
No.
No. Okay. Last questions. Do you think when a bubble flow up to the surface of the fluid, it will cause turbulence? Will it affect much?
Could you repeat again?
When the bubble flow up to the surface of the fluid, it may cause turbulence. Do you think it influence much?
Sorry, could you explain what is turbulent?
Turbulence means something may affect the flow of the fluid. Oh, okay. Skip the next questions. Do you? Okay. I have done my questions.
Okay. Opponent has 2 minutes to prepare.
opponent takes the floor.
Okay, hello ladies and gentlemen and dear juries. I'm the opponent from Team Oops. I'm Kenneth Liu. Today I'm going to talk about drinking straw. And this is our problem statement. Please skip the next page. And points per reporter. And okay, skip the next page. And pros and cons. The most important part is the cons. It is lack of mathematical model and it's not quantified. The gas quantity in the fluid. Okay, next page. And discussion, we have to discuss about the initial quantity of gas in the fluid. That makes your experiment maybe more accurate. And I agree the surface tension is more important. It's important when the straw becomes topple. It flow ups and topple, but sometimes it may not topple. It will just flow in on the fluid. It may caused by the surface tension because the surface tension drag it, and so it cannot topple out of the glass. And the third is the condition of topple. Maybe you have to explain clearly. And the fourth is the height change when the bubble eliminated. Because when your straw is floating up to the fluid, the bubble might be escape from the fluid, so it causes the difference in the buoyancy force. And I have to discuss about the velocity of the straw flow up to the fluid because the straw is flowing up to the fluid. It has a velocity. The bubble escape from the straw when it flows up because of water flow, right? And I have to discuss when the bubble is flowing up to the surface, it may cause the difference in water flow inside the glass tube. Is true. And do you think it affects much about this phenomenon? Oh, okay. And please skip to discussion. Okay, go ahead. Okay, I have to ask about your experiment. First, do you agree the quantity of the gas influence the phenomenon much?
Yes, it affects a lot.
Okay, and I have to ask about, do you think the temperature affects the phenomenon much
The temperature
of the fluid?
affects carbon dioxide.
Okay.
Also,
It influences much, right?
yes.
Okay, but I have to ask about when you change your temperature, the quantity of the gas that can get into the fluid will change, and the rate of the bubble which are attached on the straw, the rate of that might be increased, right?
Can you say it again?
I said the bubble which attached on the straw may be faster, right? And
Yes, just as I mentioned in experiment 4.
okay, but the temperature influences the quantity of the carbonate in the water, and I think it might be two variables in one experiment. And which do you think it influenced the most in the phenomenon?
We have tried to control it into one variable, so that whenever we do experiment, we pour the new etc. that haven't been opened. So we're pretty sure that our experiment only has one variable.
Okay, and I have to ask about next questions. How do you quantify in your experiment? You do about the quantity of gas in the water, which affect the phenomenon, right? And how do you quantify the quantity of the gas in the fluid in the very beginning? How do you quantify it?
We set that we think that the drinks that are sent from the factory to our hands is all the same. Like every apple cider, when it haven't opened, it will be the same. So when we open it at the same time, the amount of the carbon dioxide that will release, the rate will be the same. So we think that it doesn't. We think that we can control the rate of the carbon dioxide, the amount.
Okay, and I have to ask about the questions about your explanation. You believe that the rate of the carbonate escape from the water is a linear function, just as you say.
No, I haven't mentioned about that. I just said that as the time goes, the amount of time it takes the straw will topple will increase.
Oh, okay, thank you. And can you determine the escaping rate of the carbonate from the fluid?
It's quite hard because of temperatures and the situation. Every experiment that we did in different time will not be the same, but in the same experiment we did 2 speakers in one time. So we can be pretty sure that our experiment is correct.
Okay, and previous you talked about the surface tension is not important, right?
Yes.
But opponent believes that when the straw is blowing up, and it might not only topple out of the glass, it might be just flowing on the surface of the fluid. Do you agree?
Instead, I think that you mentioned before that turbulent. We think that it's the turbulent will affect.
I'm not asking about turbulent. I'm asking about, do you agree there might be sometimes the straw will just float it on the surface of the fluid? Do you agree?
We don't agree.
Okay, you don't agree. But at some experiment, we can observe that phenomenon. And okay, I'm going to ask about next questions. And do you agree when the straw is floating up to the surface, they will have a velocity of it?
Yes.
And do you think the velocity of it will bring bubbles out? Make the bubble which attach on the straw goes out?
We have saw some interesting during the experiment. So like when it comes up, the bubbles of the carbon dioxide will rise, but it will still attach to the wall of the straw. But if the bubble is big enough, it gets off of the wall of the straw and it will rise to the upper part of the drain.
Okay. And I have to ask about a question of your experiment. And do you think there's when a straw is flowing up the surface, there's a similar question, but a little bit different. It may cause the flow of the fluid change, right?
Yes.
And do you think the turbulence will cause much carbonate release out of the fluid? Do you agree?
Pardon, can you see it again?
Turbulence means.
I know. Yes.
Okay. And just because when the straw is floating, and it causes turbulence in the fluid, and do you agree the turbulence may cause much release of the carbonate in the water?
Yes.
Okay. And do you think the sugar water filled with carbonate is the same as pure water filled with carbonate? Opponent think it might have a little bit differences.
About that question, I've said it wrong at the first time you asked me, and I changed my opinion to, if the carbon dioxide is the same in the two different liquid. One is added sugar and one is not. I think it will be the same.
But at your previous experiment, you cannot quantify the quantity of the carbonate. How do you make sure that your statement is right?
Basically, to quantify the carbon dioxide in the drink is nearly impossible. So that what kind of device would you find the rate of the carbon dioxide?
Maybe some detecting instruments. I have heard before, but I can't talk about its name now because of some reason. Okay.
Okay, but if we need to use that device must be really expensive, and we don't have the money, and so this is considered as the technical problem.
Okay, thank you. I know. And about your hypothesis.
Yes.
Do you obtain the condition of when the straw will couple, or when will it just float up to the surface, or when will it just sink back? Or can you determine the condition between them?
In my conclusion up here, I think when there's enough carbon dioxide discharge and there's enough that causes enough buoyancy, the straw will topple.
Do you think the center of mass of the straw influence this phenomenon?
Yes.
Okay. But you have not quantified or have a model for this. So I think I suggest you to make a model, or I'm hard to believe your statement now.
Okay.
Okay. And we are going to end our discussion.
Okay.
Thanks.
The opponent summarized the discussion.
Okay, I have to summarize the discussion. First, there's a little pity that they have no much mathematical model to explain this phenomenon clearly, and they have not found the condition between between some phenomena like toppling or sinking or just floating, and they neglect the surface tension's influence. But opponents think it's important because when a straw is floating up to the surface, it may cause the surface area change. And the elementary definition of the surface tension is the energy you have to put on to change the unit area.
Question from the reviewer.
Okay, so I'm the reviewer of drinking straw from C-jeleskedik, and I think that the reporter and the opponent for bringing us up such a fruitful debate. So first of all, the reviewer would like to question two of you that what do you think is the most physical factor that causes straw to rise up in a glass of beaker?
We think it's the buoyancy,
Which is brought by
the carbon
yes.
dioxide.
What do you think?
Buoyancy, and the torch from the center.
I mean just the rise up part.
Yeah, but the torch still effect.
Okay. My next question is for the reporter. Since that you have mentioned that the bubbles will affect in the rise up motion of the straw. So and you use time to measure the volume of the dissolved bubble in the liquid, right?
Yes.
Now, so how do you make sure that so have the relationship between the time and the dissolved bubble, or how do you know that the relationship between the time and the dissolved bubble is a linear relationship?
Like I just mentioned before, in every experiment we did, the situations are different, but we can know that as the time goes.
Okay. So for you, can you elaborate more on the turbulence of the straw since you spent a lot of time on questioning the reporter?
I think the turbulence caused by the straw may cause lots of more carbonate release.
So first of all, what's the turbulence from?
Turbulence from the straw, because the straw move in the fluid, right? And it causes the different flow of the fluid, right?
Okay, so I get your meaning. So first of all, then I have a question of you two. What's your definition for tupple?
My definition of topple is when the straw goes off the beakers and moves down to the floor.
Okay, for the
And the straw flow up to the surface, and it conquer the surface tension provided
so it
by.
goes out of the container.
Right.
Yeah, okay. So for the opponent, so I would like to ask, since you spend a lot of time questioning the density of the liquid, so you think the density of the liquid will play an important role in the motion of the straw?
Density? I haven't asked about this. I asked
Oh,
about
okay.
quantity of gas.
Quantity of gas. So what do you think will change if what do you think is the main differences between a carbonated drink and a non-carbonated drink? Is that what your question?
Excuse me, I'm asking about the sugar water filled with carbonate and the pure water filled with carbonate. Is there differences between them?
Oh, okay, thank you.
Time's up. The reviewer take the floor. Oh, the opponent. Oh, preparation for the reviewer. Okay, the reviewer take the floor.
Okay, so hello, I'm the reviewer of U-苹果bang你 elasticity. So let's start with the problem statement. So based upon the problem statement, there will be two main focuses to be discussed in the issue of drinking straw. First of all, of course, the rise up part. You have to explain why the straw can rise up in a glass of carbonated drink. Then the motion, which is the part that the reviewer seeks for the discussion between the reporter and the opponent. And then there is the coupling condition for the straw. There will be three focuses to be discussed in the problem statement. Then we come to the reporter's outline. First of all, the reporter has an observation video that he observed the straw will rise up, and then he explains the theory of the coupling of the straw, which is easy to swallow, but then he comes to the experiment part. That he has such parameters such as the volume of the drink, the length of the straw, the amount of carbon dioxide, and the temperature. And he did put a lot of effort into have a lot of parameters. And then he reached a conclusion that enough carbon dioxide will make the straw easier to topple. Now, for the opponents, the reviewer recognized the effort that opponents put into the debate. First of all, he pointed out that affecting conditions of bubble, such as time, and every time you open a glass of such as the Sprite, then how to make sure the amount of bubble is remain the same in every Sprite? That's the part we have to consider. And then, of course, the dissolve rate of bubbles over time. And the second one is a quick question the factors of coupling condition, such as the effect of surface tensions. And they stated that there was a possibility that the straw will suspend at the top of a container. Since the mass of a straw is not pretty large, then there will be an effect due to the surface tension that the straw suspends. But he did not mention but the reviewer think that the effect of turbulence does not matters that much, and he did not ask for the motion of the straw. Then for the crash, does the surface tension plays a major role? And the reviewers think it does play a major role since it will make the straw suspend. Then for the temperature, the reviewer thinks that does not have too much impact on the phenomenon. When it comes to experiments, since if the temperature of a day is not that much, but if a temperature gap is pretty much, then it will make a big difference. Then its quality of a gas influence much, and the reviewer agrees with the reporter. And then the surface tension will make the straw suspend, and the reporter will agree with the opponent. And then for the buoyancy, then the reviewer thinks that the change in buoyancy is one of the factors that the reporter didn't consider, and he did not explain the motion of the straw. And then he ignored the effect of surface tension to the straw, since the surface tension can make the straw suspend. And then he didn't have a clear definition of tackle in his report. And then he ignored no force from the beaker, since the straw will touch the surface of beaker while it dries up. He didn't have it in his force diagram. And he ignored the impact of the effect of water resistance. Since water resistance will be proportional to the velocity of straw, then it will play an important role in the straw's motion. And then he ignored the density of the liquid as the opponent has questioned. And then he didn't consider the parameters that the diameter of the beaker will affect the experimental results. Thank you.
Okay, conclusion from the reporter.
Okay, so first of all, I would like to thank the opponent and the reviewer for some great suggestion about what we could do in the future. And I apologize for the surface tension. So because of we didn't investigate about the surface tension, so we shouldn't make such conclusion about the surface tension. Wouldn't change the straw's motion. And as for the reviewer just said, the diameters of the beakers that we think because of we control this thing. So we think it wouldn't in the experiment because it's all the same. So it would not consider as one of the problem. But we would do other diameters of the beakers in the future, like if we do it smaller or bigger, does it affect the motion of the straw or whether it will topple? And so thanks everybody.
Okay. Question from the jury.
There was some bubble inside the straw. So what do you think about or how to detect the bubble inside the straw, and the effect of the bubble inside the straw? What will you?
We think the bubbles inside the straw is as well the same as the bubble outside the straw. So like it's just the surface area of the thing that will affect. And every time we do a new experiment, we pull off all the drinks from the straw, so we can say that every time we put into it, the straw is clean and doesn't have any drinks in it. So we think our experiment is correct.
I think if we measure the buoyancy that the bubble brought to the straw, but since the straw will form an enlarged area around the straw, so if we measure the buoyancy with the effective cross-section area of the straw, then we times it with the underwater length of the straw, then we can ignore that if the bubbles since the bubbles will tend to attach in the outer and inner surfaces of the straw. So can I use the whiteboard to illustrate? Okay.
Similar to reviewer, just use the differences in buoyancy.
It's not done yet.
Oh, sorry.
Wait until this.
Okay, so here's the surfaces of the straw. Then since the bubbles will tend to attach on the outer and inner surfaces of the straw, then here it is bubble. Then if let's say the straw is underwater here, then according to Archimedes' principle, then we can transform it into that rho times g times the underwater length of the straw times the effective area of the straw. Then by this measurement, then we can ignore the differences between the straw will tend to attach on the outer and inner surfaces, since we measure the whole effective position area of the straw. That's what I'm trying to say. Thank you.
About me, I have a little bit differences from this master. I'll first put a straw into a pure liquid not filled with carbonate and measure the buoyancy force of it, and then put it into the water and make sure length in the foot is the same and measure the buoyancy force again. Then I can determine the volume of the bubble.
Any question?
During the discussion, the opponent mentioned that adding sugar to the carbonated water might have some physical consequence. And you change your answer to yes. So could you elaborate on the answer how the adding the sugar will change the certain physical property of the system?
What I say is as for the amount of the carbon dioxide in both drinks are the same. It doesn't matter whether it has sugar or not.
Mm-hmm.
That's what I mentioned before. So
yeah, but then you change your answer, right?
the answer I changed is about the surface tension of the straw that we didn't conclude
So you
about.
didn't change your answer. You say that adding sugar doesn't matter.
Yes.
Okay. And what about the
For
opinion
me,
of the reviewer?
since I have, according to the buoyancy formula, B equals rho GV, then if the density increases, then the buoyancy level
I'm not talking about the density. I'm not talking about adding sugar,
into the water.
into the carbonated water.
Okay, so first of all, since the water that contains sugar, it might have viscosity as the time passes, and then it might have
different viscosity.
yes.
And what else?
And yes, that's one to say. And the other one is that they might result in the increase in the density of the water.
Okay. Anything else?
And I think that's all I
That's
think.
okay. What do you have in mind when you ask?
But also, according to the reviewer's point, I want to add one. He also influenced the drag of the fluid because the density changed.
The drag, do you mean the viscosity
Or not viscosity, another form of drag. Another form of drag.
what kind? What other kind of?
You mean
like,
like
I have to.
could you drag the carbon dioxide into the water?
No, I said water drag. It's a kind of form like.
Oh, sorry.
V square.
Oh, I see.
Because the density change, and so this form will change.
Okay, I got you.
I have a question. Since all of you assume that bubble in the water that will attach to the straw that will affect the floating, the toppling rate, right? I'm going to change the contact surface of the straw.
I think that will infer to the thickness of the straw.
Yes.
And
Have you tried?
we have set our size of the straw the same, so we didn't investigate this
Okay.
phenomenon. maybe we'll do it in the future.
Okay. Okay, so for me, I think that the key factors here is that the attachment rate of bubbles according to materials.
Yeah.
So if we measure that how much centimeter should hollow free, CN, can I use the example?
I think that's you just have mentioned.
Okay, so how much bubbles will attach to the centimeter squared of the straw? If we find out the relationship, then we can know that the buoyancy of bubble grows.
I think we can change the material we use to make the straw.
It means the surface of the straw.
Yeah, we can use wood or grass or other materials.
Thank you. Okay, for the reporter. Five, 7, 6, 6, 5.
Thanks.
For the opponent, 5, 7, 7, 9, 7. You have to report again. 9 point. 5, 7, 7, 5, 9, 5. Okay. For the reviewer, 7, 8, 6, 8, 7. Okay. No problem. We have 5 minutes. Okay, reporter, take the floor.
Good afternoon, dear judges and the team. I'm from Team U. I'm the reporter David Chen. I'm reporting the cover 13 waiting time. This is my outline. First, I will do an introduction of the problem, then I'll show you the observation video, and then I'll show the theory, and then I'll show you the experiment, and that's the conclusion. This is the introduction of the problem. It is commonly known that an hourglass changes its weight as measured by a scale while flowing, so I must investigate the phenomenon. This is my observation video. As you can see the weight will change. The weight will change through time. And this is just an observation video, so we use a scale to measure it. So the scale weight changes through time, and I think that it's the normal force is time dependent, which causes the weight changes. So we can assume that the various center of the sand changes through time. The theory. We assume the center of mass is a time-dependent function z of t, and the force of the pouring sand is like that. So on the upper part of sand, we consider 4 parts. The first part is the top triangle part, and which the angle is the angle of repose alpha. And the middle arrow size part 2, lower size arrow size part 3, and the lowest part 4. But because of the lower side part 4 is so tiny, so we think we can ignore it. And about the lower part, we consider the free falling part 5, which causes the weight decrease, and the part 6, which causes the increase of weight, and height will rise through time. By the time-dependent function of center of mass of the whole system is like that. And by calculation, we can get the function from part 1 to part 6. This is an example of our calculation of part 1. So we consider the sand flows like this, and the angle is the angle of repose 2. And this is our theory. The calculation of center of mass of part 1. As you can see, the mt is the time-dependent mass through time, and the center of and the zt is the time-dependent center of mass of the decreased sand. And I'll skip to an experiment. We use 3 vernier dual variance force sensor, a vernier, Lab-Quest 2, and an hourglass. And this is our experiment setup. We use a string to connect the valve, so the valve would stop, and then we'll use a lighter to activate the valve. And then we'll use logger line to obtain the experiment data. As I said, we use 3 vernier dual range force sensor. So we'll sum the 3 data up and use the Excel to analyze the data. This is one of the data we get. And this is when we tested 4 times. But as you can see, it only exists a little constant difference because we changed a little of weight. So it's just the trend. And you can see the trend. The weight first decreases, and then it increases. Then the middle part, it will balances, and that's it will go. The weight will increase and then come to rest. I'll do my conclusion. The weight on the scale, which measures the normal force, which decreases at first, then it will balance, and then it increases, then come to rest. And the weight changes because of the center of mass of the system. This is my report.
Thank you for your report first. And can you turn to page 14? Yeah, so what is the chart? What is your chart going to talk about?
This is one of my experiment data, and I want to show you about the trend of the time-dependent weight.
Okay, so you think I think it's decreased first and then just go back to the basic value. Are you going to explain this?
Okay, as I mentioned before, the weight will decrease first, and then it will increase. And then we consider this as the balance part, and then it will increase and rest, and then come to rest.
Thank you. And Can you turn to page 7? No, sir. Yeah, and your graph part, you have marked a angle of repose, alpha.
Yeah.
So did you use it as one of your parameter?
Yes, and the experiment showed the angle of repose is 40 degrees.
Thank you. So can you restate your parameters again?
My parameters, the angle of repose is alpha, and the theta of here is 57.
No, I mean, what is your variable? Sorry, what is your variable?
Variables, I didn't change much of the variables. I just, yes, I just changed a little bit of the math. So it causes the graph of the 4 tests. Yeah, it becomes different.
Thank you.
Opponent has 3 minutes to prepare. Opponent takes the floor.
So, hi, this is the opponent from C-jeleskedik, and today I'm going to oppose the problem number 13 waiting time. And from the problem statement, after reading the problem statement, where the opponent is really curious about the tendency of the weight changing, and then we're going after realizing the trend, we're going to find out the different levels of weight changing depends on the relevant parameters. And this is a structure of solving problems. First, just like I just mentioned, we're going to know the reading of the scale change, and the reason why I chose the reading of the scale goes like this, and finally is the what factors influence this tendency. And this is the outline. And first, the reporter say about observation, and he shows the observation video, and he talked about the way will change over time, and I think the video is quite clear. And about theory part, he described things into I think several parts, many parts here. But he is lack of detailed discussion about the theory. Like I'm still not very understand why you separate it into so many different sections of time. And then it's the experiment. He used the lidar as a release device parameter, and he mentioned that he changes his names in the quick questions. And I think it's a good method to release the same, but his parameter is too little. And finally, is a conclusion. He concluded his experiment. And then I'm going to discuss with the reporter, like the theory part, what is the basic assumption of the theory, and is the flow really stable, would anything influence the flow? And then the experiment part, what kind of the scale you use in your experiments, and what parameters you change, and then influenced by any factors like air resistance and height and even flow rate. And then is the same column a basic value? And finally is the result. What is the most influential physical factor using in this experiment? And the difference of the scale, like the different scale between electronic scale or even the spring balance. And I would like to skip to the next class. Thank you. Okay, so hi reporter. And thank you for your reporter again. So I want to know, can you explain the tendency of the whole system, like the whole experiment?
Okay.
In a simple way.
Okay. Like when the sand was released and when the T is 0 and the sand was released.
Yes.
And then a part of it becomes free falling, right?
Yeah.
And so it becomes the weight decreases. And when the first sand touches the ground, it has a momentum, and it causes the weight and the weight increase. And then
your increase is to increase in the basic value, like the middle section of time, or increase above that value.
The increase.
Like in your picture.
Yeah, like this.
Oh, thank you.
Yeah, and then the upper and the lower parts, the momentum cancel out, so it becomes balanced. But in our theory, in our experiment data, it shows
Like it's not stable?
Yeah, we think that because we can consider that sand is a very small.
Okay, thank you. Can you explain do you have any, like you go back to the basic value, right? And for the last section of time, I think it's a little increase, is that?
I think when the upper sand was flow to when the upper sand flows out of the sand, so it has only the momentum but not the balance force.
Okay, thank you. Can I watch your experimental setup? So yeah, can you show video?
Okay.
So is your releasing device like you light the fire and
This is a string.
yeah. Okay. you burn the string to make it fall down.
Yeah.
Okay. So you're using electronic scale, is that right?
Yeah, the vernier dual range force sensor.
Okay. Thank you. Oh sorry. Can okay. Can you and then can you restate your variables in your variable since that the time has not enough. You have mentioned that you're just changing the mass of the thing.
Yeah, but I think because in the problem statement, investigate the phenomena because it will say the phenomena. So I think the parameters are not really that so important because it's not the. Yeah.
So sorry.
So I focus on the point on the changing weight. So I just want to show the trend about the weight.
But I'm still really curious about your. So since you have changed your mass, so do you have any results of that? Since I didn't see it in your report.
Change mass. Yes, the 4 lines are a little constant difference because of the. As you can see at the beginning, the normal force isn't the same, so we change a little mass of it.
So this test for is the same experiment in the same condition, or is you changing your weight? There's 4 different kinds of weight.
Yes, only change the weight. We only change the weight in the same condition.
Oh, so I know. So can you clarify which is the mass, which line is the way you use the most, like which is the most heaviest?
The most heaviest is the red line on the top.
Okay, so do you see any difference between these 4 experiments?
We only see constant difference, so I think it's not the influence of the change of weight.
So you think that the change of the mass didn't really influence the whole system, the whole experiment, right?
Yes.
Okay, so it would not influence the tendency of the weight. Okay, thank you. Why can you explain that? You say it will become the weight will decrease.
Yes.
And then increase and go back to a basic value, and then increase and then go back to a basic value. Is that how you're expressing?
This is balance, but not really the basic value.
Okay, balance. So why is your balance? What is your sorry?
You said the oscillation problem I said the balance was alright.
Yeah. So
we can see the sand as a small spring, and the Hooke's constant is very high, so it will give a force.
okay, thank you. So you're actually changing like 3 Newton. Your weight changes 3 Newton during the experiment. Yes. So how many cents did you use? What is the weight of the sand you use?
The weight is on the chart the range is from 9 to 10 Newton.
Okay, thank you. So we can see in the reporter's experiment, the weight changing like 3 Newton, which is really impressive. And sorry, it's too bad. So let's discuss more variables. Okay. Okay. So how do you think if we change the height of the height of the upper, the height of the upper container? If you change it, how do you think the experimental result will show like?
I think because we then do that, but I think the trend will still be the decrease and the increase, but only a little difference of the trend line, just a little bit, but the trend is still the same.
And do you think it will have like the correlation relationship thing, like if the height is more higher and the weight changing will become bigger or smaller, do you think it will affect like this?
I think the weight will change more bigger. The change will be more bigger because the height is.
If the height is higher? Okay, so the opponent thinks that if we change the height into one, consider the height as one of the parameters. So if the height gets higher, the weight changing will get bigger. So do you have any thoughts about what other parameters you can focus on?
I only focus on the weight change, so I think I just stick on the training line.
Yeah, I'm very appreciate on your experiments on the weight changing. This thing is really clear. But I think maybe we could do you have any okay? Maybe we could change the flow rate.
Yeah, maybe by changing the sands density, by the Beveridge's law, the flow rate of the sand will be different.
Yeah. So how do you think the relationship between the density of the sand and the weight changing will be?
Because when the density increase, the flow rate increase too. So maybe the weight change will be bigger.
Okay. So since you are using the electronic scale.
Yes.
Yeah. Okay. So do you think the spring? Do you know spring scale?
Yes.
Yeah. Do you think it was also a better way to estimate the phenomena?
I don't think so, because the first time we consider as the normal scale and the string scale too, but the difficulty we face is the accuracy and the data to collecting is very difficult.
Okay.
Yes.
Okay. So you're thinking that the spring scale is not a way to measure the things, that it will maybe bumping and get a ugly data.
No, it's because I cannot collect the data like.
Oh, I see. Thank you. And thank you for this question.
Okay, the review. The opponent have 1 minute to summarize.
And according to the previous discussion with the reporter, and we know that after sand release, the sand will first comes down and then rising to the above parts, and then go back to the balance, and then in that section of time, the weight will increase and then go back to the basic. And then we're just discussing some more parameters we can do in this experiment. One is the height of the upper cup, and we know that the higher height of the upper cup will get the more bigger levels of weight changing. And then the second one is the sand density, since the reporter just mentioned a formula of the Bernoulli's, and then we know that yes.
Hands up. Reviewer, you have the floor.
Well, I have some questions for the reporter here. You said that you used the fire to start the experiment, right? Do you think it might affect the sand or maybe the results?
No, I don't think so. because we use an extra like a lid or something to extend the string, so it won't burn the autographs.
What about like if you, because when you burn it, you only burn one side of the string.
No, we bound this into one string. Like it is a string, and we bound it into one string, and we'll like this.
So then, what's the other two strings beside it?
No, it's total of one string, and then we will bound it as the one string. Like this is one string, and we'll bound it into one string. So this is the one string. This is one string.
Okay, so for the other part, I know that you divide your system into 4 parts, and what's the meaning of it?
I want to calculate them because the angle of repose is the balance, the balance condition of the sand. So it should have a chain to separate to 4 parts to consider, and we have done the calculation of the 4 parts, the 3 parts.
And as for the component, I just want to make sure that, because you said that, you asked that do they have 4 meters, and you talked about the height. So can you restate what you stated about height?
If we change the height of the upper cap, the weight changing will become bigger, just like we discussed about. Yes, and I'm thinking about one more variables possible. And as the flow rate, if we change the flow rate, like we can change the funnel's diameter, right? Like, and it will change its flow rate. And as the flow rate gets bigger, and the weight changing will get more bigger too. Yeah. Thank you.
Time's up. You will have 2 minutes to prepare. Okay, then review your text a bit more. Okay, connect.
Maybe someone didn't.
Set the clock.
Feel that? Still yours? Take out. Okay.
First, I want to talk about the advantage and disadvantage of the reporter. So for the advantage, I think they have a lot of formula to prove their experiment, what is very important, and they have advanced skills on their data showing. And also, they have a very stable device, so it won't shake when during the whole experiment. So for the disadvantage of the reporter, well, we think you can explain more about your phenomenon because you only mention it for a little and then you go into the formula part. And you can try more kinds of variables. The advantage of opponent is we think you offer a lot of suggestions for the reporter, and you also ask a lot of questions, which is very important and right on the book. Okay, the disadvantage we see is that the outline you use when you're reporting isn't very clear for us to see. So the reporter's view is that first is their outline is like introduction, then observation, theory, and then conclusion. And so they think the center of mass is a time-dependent function. And they're divided into 4 parts, which is the top triangle, middle arrow, lower arrow, and the lower part. So there are hourglass, then without connecting the upper and lower parts to prevent the change in air pressure, which is I think it's very important in this experiment, and it's only a little process of change. So it says that the weight will decrease at first, and then it balances, then it increases at the end. But because their variable is the weight of the sand, and they think it doesn't change on the result. For the opponents view, they think the reporter can do the height that may change the result because it provides bigger change, and the fall rate might also affect the result. And the discussion part of the opponent asked about the theory of the reporter. So the reporter said that they think because at the first part they'll have some free falling, and so the weight will decrease. Then when the sand touches the ground, it will form a momentum so that the weight will increase. The opponents ask for other parameters, but the reporter thinks that the problem is only asking for investigation, so they don't focus on other parameters. And the opponent asks that about the height of the part. They think that the change might be more clearly, but they didn't do the experiment. And also, for opponent asks for other factors, and they think that the density might change also. And so this is their report.
Conclusion for the reporter.
I'll do a concluding report. The suggestion for the opponent is that we focus on the change in weight through time. No matter and we think that no matter what parameter, the trend of the weight change will stay the same. Only a little bit of the slope difference or something, and the height will make the weight change bigger, but it has it limits. The suggestions from reviewers, we want to say that the fire won't burn the system because it's the one spring, and we make a knot on it, and so it make one string, and we combine the 2 strings into 1 string, and the air pressure is the same in 2 containers. As you can see in my experiment devices, I didn't connect the upper and lower parts as the normal hourglass because there would be a little bit of air pressure. So I separate them because to prevent the air pressure difference. Concluding remark is that we have calculated all parts in the hourglass as well as the center of mass of the time-dependent function, and the trend will decrease first and then it will increase. In the middle part it will balance, and then increase a little bit, and then it comes to rest. Yes, this is my concluding remark. Thank you.
Okay, thank you. Now the question from Joey.
Please go to page 15.
Okay. Please write the second.
The question is for all of you, okay? 15. Next one. Okay. You can see there are a very stable oscillation.
Yes.
Yeah. Okay.
Yes.
And after the time pass, the oscillation disappear.
Yes.
Okay. So please give me a reason for such kind of phenomenon.
The oscillation, as I mentioned before, is that we assume the sand has a very big Hooke's constant material, so it will bounce and give a force upward and downwards. Yes, and so it will oscillation very balanced and continuous.
Same question for the
For the reviewer. Okay. Same question.
What we think is that because the sand was going down consciously, and so the mass should be stable in that part.
and what's the reason is keep bouncing back?
Oh, they keep bouncing back. Maybe because when the sand is falling down, and when it hit the bottom, it may like just back up and then hit the side again, and so it will have some effect on that.
So why disappear?
You mean disappear where?
Yeah, after time goes on, the oscillation disappear.
Here, the fluctuation goes disappears.
Well, we think it disappears is because in the beginning, when it's still falling, there isn't much sand on the ground yet, so it will bounce easily. So, and then when the sand keep on piling up, it will, because they will have the force, so it won't bounce like when it's empty. So so that will disappear.
I'm a C-jeleskedik reviewer, and I want to add one more point. Maybe because the flow rate coming from the upper cup is not that stable to cope this oscillation.
Have you ever considered that that's the influence from outside? Because your setup has been put on the wood.
Yes, so you can see the experiment data there is
Where did you put it?
on the desk, and so at the very beginning it is not stable because because the linear dual range force sensor is so
No problem.
yes, so
Any question?
Yeah, I have a follow-up.
yes.
Just show the next page. Yeah, so this is when, before you release the sand.
Yeah, before
And this is when all the sands are
Yeah.
bottom.
Yeah.
So, how can I understand why there's a difference between this weight and this weight?
The difference because it may be the errors of our experiment setup.
So the experimental error is about
Probably for the calibration. Yes. I think they didn't set up good calculation.
Okay, let me ask one question. Okay, let's go to the page 123. You have all the equation on? Okay. Okay. Do you understand all this?
Yes.
Okay. Really? Okay, so you just mentioned at the very end, okay, the height also influence the weight, right? Where is the height? Where you can put the height?
Height means because
There's no height in the equation, right?
the height means the height of the sand, but nonetheless is the height of the sand, so the total
mean,
mass. Yes, so the total mass means when the total mass is
the height is
Yes.
the difference between the sand and the scale.
Right. Maybe
And the way you can put the height.
in part 5, the free falling part, so the free falling part will be longer.
No, what I'm saying,
Yes.
you have all these fancy equations. Do you really understand all these equation means? And I think all of you just believe and the height
Yeah, this is
also
this is,
influence the
yeah, but then part 3 it's not relation with the height. The relation with height is the part 5, which is the free falling part. And because if you think that the free falling part gets extended, then the change of weight will be bigger. And because that is just part 3. This is like we have done the
Okay.
Yes.
Okay. And you start with something like 9 Newton, right? And you have you increase by 3 Newton. And how this equation give you 3? This number 3 Newton.
Some
Yeah, I mean you just go back to your page 15.
Yeah.
Page 15, right? You start with something like 9, and then you just there's a jump about 3, right?
Yeah.
And how this fancy equation can give you the number 3 Newton?
Those equations are just the sub values, and we must just sum them up. We combine them.
Okay, I mean maybe I'm taking too much time, and either of you can just tell us why they are how to evaluate the difference, the change. Over here it's 3, and in a simple word, not all this fancy equation. Right, change from the bottom to the top.
To the top.
About
Okay. No problem.
Okay. I think it's because of the when the sand comes out from the upper cup, and then it will have a little time as in the air, right? So it will decrease in that time. Like it didn't have the when it go back to balance, it's because it gives the impulse to the bottom cup per unit of time, and in the meanwhile we have the sand in the air, which is not measured by the scale. But in the first section of time, the thing will just in the air, and there is no impulse given to the scale per unit of time. So I think that's why the weight changing decrease. And one more point to discuss. I think 3 Newton is too big.
Okay, thank you.
As for us, we can't really explain what the 3 is because it's from
No, I'm not talking about
Yeah.
the 3, and
So-
I'm talking about how, any simple word, just to tell us this is, I mean this
why
is,
it is.
right, this 1/3, right? So 30% change, right? If
You mean about
you
the
start
price?
with 9 and then you change by 3, it's about 30% change.
Yes. What I think is because when the sand is falling, there will be an acceleration. So, but when it hits the bottom, it should turn back into silent form. So there must be a force to make it back from that speed back to silent. So that's when there will be an increase in mass.
Okay.
Jury, please. For the reporter, 56455. Okay. For the reviewer, opponent, sorry, always confused. 76667.
Thank you.
For the reviewer, 66568. Okay.